Okay, so this is Chem 107, exam 2 prep. So I made this document right here with a couple problems from the workbook and that we were given in class as well as office hours. Um, I'm gonna try to, explain how we solve these on video. Just a little explanation video. So for this video, I'm just gonna be focusing on limiting reactants. So we have these two problems that were given to us. So the first one was given to us in class. Second one was given to us in office hours. I'll scroll down here. Well, let's go ahead and begin. So, before we begin, first you need to be very familiar, be very quick. You got to memorize page 50. The different conversions between the states of matter and reaction, and page 56, which is obviously how to solve this type of problem. So to begin, always, always, always assume that the equation is not balanced. So let's go ahead and just balance it or verify that it is already balanced. So we have, going from left to right, we have 1 nickel on the left side, and we have 1 nickel on the right side. Okay, so nickel's balanced. Okay, moving on. So we have HBr. We notice that HBr gets split up on the right side. So what I like to do is do this as H plus Br. So now going from left to right, we have 1 H here and 2 H's there. They're not balanced, so let's double this left side. So now we have 2 H's and 2 H's. Okay, cool. Now because H and Br are together, we have 2 H's, so we also have 2 Brs. And we have 2 Brs on the right side, so we have balanced the equation. So I'll just rewrite this on the bottom. So NiS plus 2 HBr aqueous reacts and forms NiBr2 aqueous and H2 gas. Now for every blank, let's just put in a 1 just to make it easier later on. Okay. And now we have this giant block of text, and it can be a little bit overwhelming to look at. So let's just look at this and be like, okay, well, what is it telling us? Well, it's giving us some values of the reaction, and then we can go ahead and input this underneath the corresponding term. So for example, we have right here, we have 1.02 grams of nickel. So right here under nickel, we can do 1.02 grams of nickel reacts with 750 milliliters of a 0.112 molar HBr solution. So let's do 750 milliliters of a 0.112 molar HBr solution. So these are going to react. And it's asking us how much of each will be present at the end of the reaction. So how much of each at the end of the reaction. Now notice it also says if you capture the gas in a 2.50 liter vessel at 30 degrees Celsius, what is the percent yield if you collect 0.0910 atmospheres of the gas? Let's do this to make it easy. If you capture the gas in okay. So this is talking about the gas specifically, which the gas in this scenario would be hydrogen. Since it's on the reactant side, let's just write this on the reactant side. So for gas, it's asking us what is the percent yield if 0.0910 atmospheres were collected, and that gas was collected in a 2.50 liter container vessel. I'll just say container at 30 degrees Celsius. Okay. And then just the last part, assume the volume does not change. So whatever volumes we start with, that's the amount of volume that we end with. We'll just say V is constant. This will come back later. Okay. Cool. So now it's a little bit simpler to see what we're trying to do here. So if you recall from page 56, step 1 of a limiting reactant problem is to make sure you have a limiting reactant problem. So how do we do that? Well, from the name, limiting reactant, if we have more than one reactant, then we have a limiting reactant because one of them is going to have to run out first, right? You know, if you're making a sandwich, right, you got your bread, you got your cheese, and you got your ham, and then, you know, any other ingredients, right? You have multiple ingredients, so the entire reaction, the amount of sandwiches you can make is going to depend on which ingredient is going to run out first. Like, for example, you got, well, you know, you get the analogy. Okay. Well, step one is, do we have more than one reactant? And yes, we do. So we do, in fact, have a limiting reactant problem because there's two of them. Okay. You know, one of them's going to run out first. Okay. Well, step two is we're going to pick a product. I'm going to pick H2 because it's less things to write. Okay. So now step three is we need to find what the limiting reactant is. Okay, so between Ni and HBr, which one of those two is going to run out first? And so how do we do that? Well, we just find each product, how much H2 will each product make individually, and we will just compare two values. So for 3A, let's just do step 3A. Let's do nickel because left to right. So we begin with our given value. So we were given 1.02 grams of nickel. And so and we need to convert this to moles of nickel, so it's easy to work with. If you recall, our conversion factor would be the molar mass, and the molar mass would be the number on the periodic table over 1 mole. So Ni on the periodic table gives us a molar mass of 58.71 grams per 1 mole. Since we already know the amount of grams and we want to find out how many moles we have, we will just flip this conversion factor. So 58.71 grams of nickel is on the bottom. That's going to cancel with grams of nickel on the top. That's going to be 1 mole. Okay. So this number, and I will pull up my calculator for this. Okay, I'll just go ahead and clear this out. Okay. So we have 1.02 grams of nickel, and it's going to be multiplied by 1 over 58.71 grams. That's going to give us 0.017, and I'm going to round to 3 significant figures because if you read the problem, we only use 3 significant figures. Oops. So 174 moles of nickel. This, okay. So now from this, we want to find X, or let's say Y, the moles of H2. So so we need to know the conversion factor. So what is it? It's going to be our molar ratio. So what's our molar ratio? Okay. Well, assuming you have a balanced chemical formula, which we do, the molar ratio between substance A and substance B is going to be the coefficient of the substance in the balanced formula. For example, nickel, right? We have X moles of nickel, and we want to convert that to Y moles of H2. Okay. So we know that the conversion factor is going to be the ratio of their coefficients from the balanced formula. So Ni has a coefficient of 1, and H2 has a coefficient of 1. So in other words, for every 1 mole of Ni, we produce 1 mole of H2. And the reverse is also true. For every 1 mole of H2 that gets produced, we have 1 mole of Ni that reacts. Simply stated, this number right here, 0.0174, we're going to multiply that by our conversion factor of 1 mole of nickel and 1 mole of H2. 0.0174 times 1 is 0.174, and that divided by 1 is 0.0174. So we just canceled out the units, so 1 mole of nickel cancels out with the moles of this amount of moles of nickel. That's going to give us moles of H2. This is how much it gets produced from nickel. Okay, so now part B, we do the same thing, but instead of nickel, we use the HBr solution. So how much HBr do we start with? Well, we have 750 milliliters of a 0.112 molar HBr solution. Okay, so what is that in moles? Well, if you remember, molarity is really just the X moles of solvent or solute over Y liters of solution. Let me just double check, because I confuse solvent and solute. So solute versus solvent. Solute is the substance being dissolved, so yes, that was correct. So in this case, right, we just plug in the numbers that we already know. So we know that we have 0.112 X moles of our solute, which is HBr, divided by our liters of solution, right? Okay, and that's going to equal to X moles of HBr over 750 milliliters. Now we need to convert milliliters to liters first, which 750 milliliters, we know that 1 liter is the same as 10 to the 3 milliliters. That's going to give us 0.750 liters. Okay, so I'm going to erase this part right here. So we know that 0.112 X moles of HBr over liters of solution is equal to X moles of HBr over 0.750 liters of solution. Liters of solution. Okay. So in order to find X moles of HBr, we can just multiply both sides by our volume. So we have 0.112 times X moles of HBr over liters of solution times 0.750 liters of solution is equal to X moles of HBr. Notice that our units cancel. Liters of solution cancels with liters of solution here. So cleaning this up a little bit more. Gonna erase this top part. So we say that 0.112 times 0.750 moles of HBr. Oh, we complete the calculation. We'll put this into our calculator. So that's going to give us 0.112 times 0.750. That's going to give us 0. I erased wrong. Okay. 0.0840 moles of HBr. 0.84. Okay. Again, I just added 0 because 3 significant figures. So now we have moles of HBr, and let's convert that to moles of H2 using our molar ratio. So we have 0.0840 moles of HBr. We're going to multiply that by our conversion factor, which is our molar ratio. So we have for every 1 mole of H2, there will be 2 moles of HBr. Okay, putting that in our calculator, we have 0.0840 divided by, or we can multiply that by 1 divided by 2. That's going to give us 0.0420 moles of H2. So to find the limiting reactant, we just compare both answers, and whichever one produces the smaller number is the limiting reactant. So I'm going to go ahead and highlight the numbers. So from nickel, we produced 0.0174 moles of hydrogen gas. And then from HBr, we produced 0.042 moles of hydrogen gas. 0.0174 is smaller than 0.042. So step 4, we simply state that nickel is the limiting reactant. I'm going to abbreviate it as LR. Okay. So now step 5, using that limiting reactant that we just found, how much of the other products will we form? Well, we already found H2, so we just need to find how much NiBr2 are we going to produce. Same as before. So we have 0.0174 moles of nickel. And to convert that to moles of NiBr2, we use our molar ratio. So for every 1 mole of NiBr2, we have 1 mole of nickel. And, something times 1 over 1 is just itself. So we have 0.0174 moles of NiBr2. Cool. Okay, let's just box this in. And let's just highlight it. Let's just highlight it green. We're going to need this number for later. Same thing up here. Since H2 is our limiting reactant, we're just going to box that in. We're going to box in the value of H2 that gets produced by our limiting reactant. So I'm just going to highlight that green. We need that for later. Okay. So step 6 is... Well, steps 6 and 7 are just going to be finding how much of the other reactant is going to be left over. So before we do any calculation, right, let's just think about this really quickly, okay? Ni is our limiting reactant, meaning that once the reaction takes place, Ni is going to completely run out. Since Ni is going to run out, we assume that since that some HBr is going to be left over, correct? For example, if you're making a sandwich, right? You run out of bread, okay? Well, you're probably going to have some cheese, some lettuce, some ham left over. So we need to find how much of those other things are left over. And so what I like to write is just this thing. So amount that you started with, so amount started, minus the amount that you used. Oh my goodness. Minus the amount you used is equal to the amount that was left over of that specific ingredient. Okay. So we know how much we started with, so how do we know how much we used, right? We know this number that was given to us right here, 750 milliliters of an HBr solution, and we converted that to this amount of moles of HBr, okay? So we need to find how much we used. So similar to steps 3, 4, and 5, we just use our molar ratio. So we started with 0.0174 moles of Ni. Using our molar ratio, we know that for every 2 moles of HBr, there's going to be 1 mole of Ni. So we have 0.0174 times 2 over 1 0.0348 moles of HBr. Okay, so what does this number mean? This means that whenever our amount of Ni runs out, right, when we finally use up the 0.0174 moles of Ni that we had, we will have used 0.0348 moles of HBr. So this is going to be our used portion of the formula. So if you recall, right, started minus used equals leftover, so that's step 7. So how much did we start with? Well, we found this earlier when we converted the solution into moles. We started with 0.0840. So 0.0840 moles of HBr minus the amount that we used. So we used 0.0348 moles of HBr. So put this into a calculator. 0.0840 minus 0.0348. That's going to give us 0.0492 moles of HBr left over. Or we can also call this our excess. So we have an excess of this much. So let's just box that and highlight it. We're going to need this later. Okay. Maybe not this top part. I'm just going to highlight this part right here. Okay. I'm going to reference it later. Okay. So now we went down the line. So we did Ni, HBr, NiBr2. So now H2. So what you do, so for H2, because it is a gas, we need to remember the ideal gas law. So ideal gas law, which is pressure times volume is equal to moles of substance times the gas constant times the temperature in Kelvin. Okay. So we know we want to find how much gas we made. Well, the theoretical amount of gas that we can make. So we will plug in all of these values, all the values that were given to us, this right here. So using a different color. For the gas, this is if you capture the gas, so specifically the gas is 250 liters. Okay, liters is volume. At 30 degrees Celsius, that's temperature. And then R is a constant, right? It's always 0.08206 liters times atmosphere over Kelvin times moles. And N, well, that's what we found in step 3, this right here. Because the amount of hydrogen gas that we can produce is going to be limited by how much nickel, because nickel is going to be the first thing we run out. So once we run out of nickel, there's nothing more we can make because there's no more ingredients, right? You can't make a sandwich if you ran out of bread, right? You can, I guess you could make a sandwich with like a lettuce wrap or something, but if you run out of bread, you can't make a sandwich anymore. So the amount of sandwiches you can make is limited by the amount of bread you have in this scenario. Okay. So going back down, step 8. So PV equals nRT. We're just gonna substitute the values that we already know. So P times 2.50 liters is equal to the moles, which was 0.0174 moles of hydrogen gas times our gas constant is going to be 0.08206 liters times atmospheres over Kelvin times moles. And we're going to and then we multiply this by our temperature, which was 30 degrees Celsius but we need to express in PV nRT. It has to be in terms of Kelvin, so we just add 273. So it's going to be 303 Kelvin. So 303. Okay. So we want to find our theoretical pressure. So I'm going to label this PT for P theoretical. And so in order to find this, right, we isolate the variable. So we do 0.0174 moles of hydrogen gas times our R constant 0.08206 liter atmospheres over Kelvin times moles times 303 Kelvin over 2.50 liters. Okay, so first let's just cancel out all of our units, just to prove that we are indeed finding the pressure. So we have moles of H2 here, so moles here will cancel with the moles here on the bottom. Kelvin here is going to cancel with the Kelvin there. Then liters at the bottom is going to cancel with the liters up there. So we're just left with atmospheres, which is our unit of pressure. So indeed we are finding pressure. So P theoretical is equal to 0.0174 times 0.08206 atmospheres times 303 over 2.50. So we just plug this number into the calculator, 0.0174. 0.0174 times 0.08206 times 303 all over 2.50. That's going to give us 0.174 atmospheres. So P theoretical is equal to 0.174 atmospheres of hydrogen gas. Okay. Now, when we go back up to the problem, it was asking us for what is the percent yield if you collected 0.0910 atmospheres of the gas. So what does that mean? Okay. Well, we found the theoretical pressure, right, on paper, but once you do this reaction in a lab somewhere, in real life, obviously there's going to be some error, and so you might not always get your theoretical value. You might get something slightly below that. And so we measure how effective our reaction was in terms of percent yield, right? So out of the theoretical amount that I could have gotten, what percentage of that did I actually get in the reaction? And so the way that we find this is percent yield is equal to your actual value over your theoretical value. Theoretical times 100%. Okay. So in this case, right, we have P actual over P theoretical. So we're just going to substitute that. So P actual was 0.0910 atmospheres of H2 over our P theoretical, which we just found to be 0.174 atmospheres of H2. So atmospheres of H2 cancel out. We run the calculation, 0.0910 divided by 0.174. It's going to give us that number, and then we multiply by 100 to find the percentage. So that means that we had a 52 point I believe I got a different number earlier. 0.0910. Oh, I see what I did wrong. Okay, so it's going to give us... Sorry, I did this problem earlier and I got a different number, so I'm just going to double check this. Double check our math. 0.0. So he did 0.0174 times 0.08206 times 303. No, that gets divided by 2.5. This could be. Oh, sorry, I apologize. I rounded up to the wrong number. I didn't need to round that. Okay. See, always make sure your rounding is correct. So 0.0910 divided by 0.173. And then we'll multiply that by 100 to give us 52.6% yield. See, that was a difference of almost, so of four values. Anyways, okay, so that's our percent yield. Just box that in. We're gonna need it for this final step. Okay. And also, if you want to box in what our theoretical pressure was, which is this part right here, we're also going to need this later. Okay, that's step 8. So step 9, we just put this all together. Okay. So for step 9, there's 5 things that we put down. One was obviously the amount of all of the reactants left over, or of all the things left over. So we need to say how much was left over of nickel, how much was left over of HBr, how much was left over of NiBr2, and how much was left of H2 at the end of the reaction. And then the 5th thing that we need to put down is, it just depends on what you did for step 8. For example, step 8, you're going to be asked one of 2 questions. Either for step 8, I'm just going to write this in red off to the side over here. There's two possible questions that they will ask you. So there's either if X amount of product A gets made, then what is the percent yield of the reaction? Or if the percent yield was X, then how much or value Y of substance B was made. And so, in our case, we did case A, where X amount of atmospheres was produced, and we had to find the percent yield. So in step 9, we're going to write down the percent yield. If it was the other way, if we were given 52.6% yield, how much gas was produced, then we would write how much gas. We would write our P actual. But since we were given P actual and we figured out P theoretical, we just need to express the percent yield of that. So again, the first 4 things are going to be just all of the ingredients, how much is left over. So nickel, starting with nickel because it was on the left side, is our limiting reactant. So we are left with 0 grams of nickel. Why grams? Because in the problem we were given, I have no clue what I just did. I just erased everything. Okay. Because in our problem, we were given nickel in terms of grams. So whatever you were given, whatever state of matter it was given in at the beginning, you're going to have to state that at the end in step 9. Okay. So 0 grams of nickel left over because those are limiting reactant, right? Because those are limiting reactant. You don't have to specify that, but Anyways, moving on to the next one, which was HBr. Remember, HBr, there's going to be some amount left over, right? Because Ni ran out and it used up a certain amount of HBr, and we subtract that amount that was used from the amount we started with, and that's going to give us how much we were left over at the end of the problem, or at the end of the reaction, or in other words, our excess amount, which was 0.0492 moles of HBr. Now, before you write this down, right, so 0.0492 moles of HBr. So remember, what state of matter was HBr given in? And that would be aqueous. It was given as an aqueous solution, which is expressed in terms of molarity. So we need to convert this number into the molarity of an HBr solution. So remember our definition, molarity is equal to X moles of solute over Y liters of solution. Okay, well, we know how many moles we have, so we have 0.0492 moles of HBr, and we're going to divide it by our liters of solution. Well, how much liters of solution do we have? You recall from the problem, the volume does not change. So what volume do we use? Well, the one we were given, 750 milliliters. Sorry, it's getting a little bit hard to read this part right here, so I'll just go ahead and erase all of this. We want to find the volume does not change, and we were given a volume of 750 milliliters. Okay, well, 750 milliliters, we need to convert that to liters, which we have previously stated was 0.75 liters. So pulling up the calculator again, 0.0492 divided by 0.75 is going to give us 0.0656 molar solution of HBr. So we're going to go ahead and write that down. I'll express this in scientific notation, just personal preference. 6.56 times 10 to the negative 2 molar solution of HBr. E to the E negative 2, or E minus 2 is the same as 10 to the negative 2 power. I just write E to negative 2. It's quicker for me. Okay. So that's HBr. So next is NiBr2. And we found that in step 5. That's going to be 0.0174 moles of NiBr2. Remember, this was an aqueous, so it's a solution, so we can express it in terms of molarity. So 0.0174 moles of NiBr2 divided by the same volume, 750 milliliters, so 0.75 liters. That's going to give us, so 0.0174 divided by 0.75. That's going to give us 0.0232 molar solution of NiBr2. Cool. So on our left side, on our step 9, we're going to write, again, in scientific notation, 2.32 e to the, or not e, sorry, 10 to the negative 2 molar solution of NiBr2. Okay, now the fourth thing is going to be gas, which in this case we had to find our theoretical value, so we will write down PT, which was 1.74 times 10 to the negative 1 atmospheres of hydrogen gas. And now, so we found all of our ingredients. Now, the fifth and final thing we have to write down is the operation we had to do in step 8, which we had to find the percent yield. So we will just write down 52.6% yield. And we're going to box this section because this is the part that the doctor will look at when she's grading the exam. So I'll just highlight this to make it stand out. This is our end result. This is how much we got, how much of each thing was left at the end of the reaction, plus what the percent yield was, as they asked us to do. Okay. And just to prove that this is correct, this is the answer. This is the answer Dr. Wen gave us in class. And you can compare the answers. Okay, cool. Moving on to number 2. I actually haven't done this one yet, so for this one, let's do a challenge. Dr. Wen says that we have to do this in about 15 minutes, or faster if we can. So what I'm going to do is I'm going to set up a 15-minute timer. And I'm just going to try to solve this as quickly as possible. You can try to follow along. I'm just going to be saying the steps or my thinking out loud so you guys can hear what I'm thinking. Get your pencil ready if you want to follow along, and I'll begin. Okay. So first, let's balance our equation. Well, first, let's make sure it's balanced. Okay. We have one ale here. Oops. My pencil. Okay. We have one aluminum here, one aluminum there. Cool. Okay. Well, here we have 3 NO3s, and here we only have 1, so we're going to triple this. Okay, so now we have 3 H's, but only 2. Okay, well, we're going to multiply this by 3, and we're going to multiply this by 6. So now we have 6 H's and 6 H's here. Okay. Now we have 6 NO3s, but we only have 3 here, so we're going to So 6 divided by 3 is 2. So we're going to go ahead and double this. Okay, so now we have 2 aluminums. We only have 1 aluminum here, so we're going to go ahead and double that. So now 2 aluminums on the left side, 2 aluminums on the right side. 6 hydrogens on the left side, 6 hydrogens on the right side. 6 NO3s on the left side, and 6 NO3s on the right side. So we have a balanced equation now. Okay, we're just going to rewrite this as 2ALS plus 6HNO3 gas. It's going to react and form 3H2 gas plus 2AlNO3 aqueous. Okay, so now we're going to put in our given values underneath them. So we start with 0.575 grams of aluminum, reacts with 601 milliliters of a 1.21 molar HNO3 solution. So those are going to react, and we want to know how much of each. And we know that the reaction had a 75.1% yield, and the reaction took place under 275 Kelvin and 0.55 atmospheres. Okay. Cool. All right. So step 1, do we have more than one reactant? Yes, we do. So we do indeed have a limiting reactant problem. Step 2, let's pick a product. I'll do H2. Again, it's quicker to write. So step 3A, we're going to find the limiting reactant. So let's start with aluminum. So we have 0.575 grams of aluminum. Our molar mass is 1 mole per, according to the periodic table, 26.9815 grams of aluminum. That's going to give us moles of aluminum. So it equals to 0.575 divided by 26.9815. That's going to give us, why is this thing? That's going to give us 0.0213 moles of aluminum. Okay. Using our molar ratio, we know that for every 2 moles of aluminum, we have 3 moles of hydrogen gas. So once we do that conversion, so we have 0.0213 times 3 over 2. That's going to give us 0.031320 moles of hydrogen gas. Okay, so step 3b, we do the same thing, but this time with the other reactant. So we have 601 milliliters of a solution. 601 milliliters. Let's convert this to liters. So one liter of solution is the same as 10 to the 3 milliliters of solution. So that's going to give us our liters of solution, and we recall that liters times the molarity is going to give us the moles of the solute. So we do that, and we multiply that by 1.21 moles of HNO3 over liters of solution. Okay, well, our milliliters cancel and our liters of solution cancel. Okay, so that's going to give us so 601 times 1 over 10 to the 3 times 1.21. It's going to give us 0.727 moles of HNO3. Cool. So now 0.727 moles of HNO3. Using our molar ratio, we know that for every 6 moles of HNO3, we have 3 moles of H2. We can simplify 3 over 6 as 1 over 2. So we have 0.727 times, we can just divide it by 2, 3635, and if you don't believe me, we can do the other way, 0.727 times 3 over 6. Okay, so we have 0.364 moles of H2 produced. Okay, so step 4 is just which one of these two gives us a smaller number. So this gives us, so aluminum gives us 0.0320. HNO3 gives us 0.364, so aluminum is going to be our limiting reactant. Aluminum is the limiting reactant. Okay. Step 5, using that limiting reactant, how much of the other products will we form? Okay, so how many moles of aluminum do we have? We have 0.0213 moles of aluminum with our molar ratio. For every 2 moles of AlNO3, we have 2 moles of aluminum, so it's going to be a 2 mole AlNO3 and 2 moles of aluminum. 2 over 2 cancels out, so we have 0.0213 moles of AlNO3. Okay. So now step 6. We need to find how much of our other reactant is left over. We need to find our excess. So first we need to find how much gets used up. So for that, we start again with 0.0213 moles of aluminum, and our molar ratio for every for every 6 moles of HNO3, there's going to be 2 moles of aluminum. In this case, 6 over 2 simplifies to 3, so we can just do 0.0213 times 3. To go to that, I can do it the other way if you don't believe me. 0.213 times 6 over 2. Okay, that's going to equal 0.0639 moles of HNO3. This is going to be used. Okay, so step 7, remember, started minus used is equal to leftover. Okay, so how much HNO3 did we start with? Well, we started with this much. So 0.727 moles of HNO3 minus 0.0639 moles of HNO3 is equal to, it's going to equal to our leftover, so 0.727 minus 0.0639 is going to equal to 0.663 moles of HNO3 leftover, or we can call it our excess. Box that in. We're going to need that for later. Oh my goodness. Okay. Step 8. We're going to be dealing with the gas, right? Okay. So remember, ideal gas law, PV equals nRT. Okay, well, we know N, we know T, and we know, here, let me write it down. So PV equals nRT. I'm just going to go ahead and highlight the numbers that we know. That's T. R we already know. N we found, and P is we already know. So we're solving for volume. Okay. So going back down to step 8. Okay, so PV equals nRT. Let's just plug in the values that we already know. So it was collected at 0.55 atmospheres. I forgot to write it down here. I apologize. So 0.55 atmospheres of H2 times our volume is equal to our moles of H2 produced, which we get that from 3A, 0.727. Or sorry, from 3A we get that as 0.0320. Remember how I said, box and highlight the important things? That is why. 0.0320, 0.0320 moles of H2 times R, which is going to be 0.08206 liters times atmosphere over Kelvin times moles. And then we're going to multiply that by our temperature, which we said was 275 Kelvin. Easy, so no conversion for that. 75 K. Okay. So isolating the variable, volume, or theoretical volume, is equal to 0.0320 moles of H2 times 0.08206 liter atmospheres over Kelvin mole times 275 Kelvin over 0.55 atmospheres of H2. Okay. So atmospheres cancel, Kelvin cancels, and moles cancel. So so that only leaves us with liters of H2. So we are indeed correct with our calculations so far. So let's do 0.32 times 0.0208 times 275, all of that over 0.55. So that means that our theoretical volume is equal to 13 I'm going to break the rules right here. I'm just going to go 13.13 liters of H2. Okay. I'm just going to insert a page. Home, insert a page. Okay. Okay, so now that we know that, we're going to find our, well, if we refer to our earlier example, we know our percent yield. So our percent, goodness, draw, was 75.1%. So we had a 75.1% yield. Okay, so the recording stopped. I had run out of storage. I cleared that up. So at the same time, I had run out of time. So, you know, we got to be a little bit quicker than that. But, you know, just to finish the problem, let's, I'll set up a stopwatch and see by, you know, by how much we are over. So let's go ahead and start. Going back to our problem. So we have, so if you remember, percent yield is equal to your actual over your theoretical times 100. Okay. Well, if we already know what the percent yield is, right? So first thing we should do is 75.1% is divided by 100%. So the percents cancel. And so 75.1 divided by 100 is equal to 0.751. Okay, so it's equal to 0.751. So 0.751 is equal to our actual over our theoretical. Okay, well, we know what our theoretical is. It was 13.13, so 0.751 is equal to our, let's just call this our VA over our V theoretical, which was 13.13 liters of H2. Okay. Now to isolate the variable, right, 0.751 times 13.13 liters of H2 is equal to our actual volume, VA. So 0.751 times 13.13 is equal to 9.86 liters of H2. Okay. And then we can verify this by plugging this back in reverse. So 9.86 divided by 13.13 is equal to that times 100 for a 75.1% yield. All right, so, cool. So that's step 8. We're going to box this in. So step 9, we just write all of this down. Okay. So left to right, Al was our limiting reactant, and it was a solid. So we're left with 0 grams of aluminum. Cool. HNO3. HNO3 is our excess, so 0.663. Remember, it was an aqueous solution, so 0.663. Remember, this is an aqueous solution, so we need to find that in terms of molarity. So moles of that over liters of solution. Okay, well, how many liters do we have? 601 milliliters, so 0.601. So 0.601 liters of solution. So that's going to give us 0.663 divided by 0.601. This is going to give us 1.10 molar HNO3 solution. So we can just write 1.10 molar HNO3. Okay. Moving on, we have H2 gas, which, let's skip that one for right now. Let's do AlNO3. So AlNO3 is equal to this one right here. So 0.0213 moles of AlNO3 divided by same volume, 0.601 liters of solution. So that's going to give us 0.0213 divided by 0.601. That's going to give us a 0.0354 molar solution of AlNO3. Let's just express this in scientific notation. 3.54 times 10 to the negative 2 molar AlNO3. Now our gas, it's asking us how much of each will be present at the end of the reaction if the reaction has a 75% yield. So remember, before it was asking us, okay, if this much was made, what's our percent yield? This was the reverse. This was the percent yield. How much was actually made? And in this case, it was 9.86 liters. So we'll just write that as 9.86 liters of H2. Okay. It was actually produced, and oh my goodness, why is it not? That. Okay. And now the fifth thing was, okay, what's the last thing we need to write down? So we got 1, 2, 3, 4. So if the reaction has 75.1% yield, take place. Let's see, back up here, let's see what they said here. So what is the percent yield if you collect? Well, it's not changed. We were asked to find our theoretical volume, so we'll just say VT for V theoretical is equal to 13.13 liters of H2. And then we can specify here at the top what V actual was, since it was also not given to us, where V actual is equal to 9.86 liters of H2. We box that in, and we're done. So about 7.5 minutes over, you know. Obviously, the more you do this, the faster it's going to come. There's going to be certain shortcuts that you will spot. But, you know, this is what I got. You know, I have not verified this with anybody. If you got a different answer, please let me know so we can all learn from this. But yeah, that's limiting reactants with, you know, gases and solutions and solids, all the states of matter. We did that, and then so I hope this helped. If you have any questions or if there's corrections, you know, obviously let me know. We're all here to learn, and well, good luck on the exam.